The manifold pressure gauge climbs past 60 inches, 62, 65. Captain Robert S. Johnson's gloved hand pushes the throttle forward one more notch, feeling the Pratt and Whitney R 2800 engine respond with a deep rumbling surge. It's February 17th, 1944, 28,000 feet above Brunswick, Germany, and the temperature outside hovers at minus 40 degrees Celsius. Below him, 150 B-17s lumber toward their target, black puffs of flak already dotting the sky. Above him, 30 Messerschmitt Bf 109s dive from 35,000 feet. Johnson checks his fuel gauge. The liquid in his main tank isn't the standard green-dyed 100/130 octane that powered the 8th Air Force through 1943. This fuel glows purple in the sunlight streaming through his canopy. Purple passion, the ground crews call it. 100/150 octane, experimental, unproven in sustained combat, and, according to 3 separate engineering reports filed between June and December 1943, potentially catastrophic to engine longevity. He keys his radio. Keyworth yellow flight, bandits high at 2 o'clock, climbing to engage. The P-47 responds like it's been shot at from a catapult. 2,800 feet per minute, 3,000. Johnson's rate of climb indicator swings past numbers he's never seen in 18 months of combat flying. The Messerschmitts are diving at 400 miles per hour. He's climbing at almost the same rate they're descending. For the first time in his combat career, altitude advantage isn't a prayer, it's a certainty. What Robert S. Johnson doesn't know, what none of the pilots testing Purple Passion fuel know, is that 6 months earlier, a heated argument in a conference room at Wright-Patterson Army Airfield in Ohio nearly killed this innovation before a single test flight. The fuel he's burning was rejected twice by procurement boards. The chemical formula was deemed too expensive. The manufacturing process was declared impossible to scale, and the chief engineer at Standard Oil called it a solution in search of a problem. But in January 1944, desperation changed everything. Because the Luftwaffe was killing American bomber crews faster than factories could replace them, and the P-47, America's heaviest and most expensive fighter, couldn't climb fast enough to stop the slaughter. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. And this is the story of how one fuel became the difference between air superiority and catastrophe, how a rejected chemical formula gave the Thunderbolt the performance it was always supposed to have, and how the men who flew with Purple Passion discovered that sometimes the right answer requires burning the rulebook. Section 2. Building the world. The problem begins in May 1940, when the Royal Air Force is bleeding aircraft over France. Hurricane and Spitfire pilots report the same frustration with mechanical consistency. German Messerschmitt Bf 109s climb higher, fly faster, and escape at will. British pilots can hold their own in turning dogfights, but the Germans have the initiative. When Luftwaffe pilots find themselves in danger, they use their 20 to 30 mile-per-hour speed advantage to dash to safety. The culprit isn't pilot skill or aircraft design, it's fuel. RAF fighters in spring 1940 burn 81/87 octane gasoline. The Luftwaffe fills their tanks with 91/100. The difference means German engines generate more horsepower without detonating. More horsepower means more speed means control of the engagement. By June 1940, the solution arrives from across the Atlantic. American refineries, led by Standard Oil and Shell, ship 100-octane fuel to Britain. The Rolls-Royce Merlin, the 12 engine, designed specifically for this higher-octane fuel, enters service in Spitfire Mark IIs. By the end of 1940, RAF fighter engines powered by American fuel match German performance. The Battle of Britain becomes survivable. But 100 octane is merely the beginning of an arms race measured in chemical formulas. The octane rating system, developed in the 1920s, measures fuel's resistance to premature detonation. Pure iso-octane receives a rating of 100. Fuels exceeding 100 receive performance numbers based on how much power they enable beyond the iso-octane baseline. 100/130 fuel means 100 octane at lean mixture settings used for cruise, and a performance number of 130 at rich mixture settings used for takeoff and combat. The first number measures anti-knock quality during economical flight. The second number measures anti-knock quality when the pilot pushes the throttle forward and dumps extra fuel into the combustion chamber for maximum power. The richer the mixture, the more cooling effect, the higher the manifold pressure the engine can tolerate without destroying itself through detonation. By 1942, American fighters standardize on 100/130 octane fuel. It's a massive leap from pre-war 87 octane, but Germany responds. By late 1942, Luftwaffe fighters burn C3 fuel, roughly equivalent to 100/130. The performance gap closes. The advantage disappears. And then comes the P-47. The Republic P-47 Thunderbolt enters service in April 1943 as the heaviest single-engine fighter in the world, 12,000 pounds fully loaded, 7 tons of aluminum, steel and firepower. The aircraft is built around the Pratt and Whitney R 2800 double wasp, an 18-cylinder radial engine producing 2,000 horsepower. To harness that power at high altitude, Republic engineers add a General Electric turbo supercharger in the rear fuselage, requiring hundreds of feet of ducting that bloat the aircraft to the size of a small bomber. The performance is impressive. 430 miles per hour at 25,000 feet, 8 50 caliber machine guns, armor protection that lets pilots survive hits that would down any other fighter. But the weight creates a fatal problem. The climb rate is dismal, 2,100 feet per minute in early models, barely better than fighters half its size. On April 15th, 1943, Major Don Blakesley leads the 56th Fighter Group's first combat mission over France. His after-action report is blunt. We can catch them in a dive, but they climb away before we can get into position. The 8th Air Force bomber crews, bleeding losses at catastrophic rates, don't hide their frustration. Without fighters at altitude, when attacks begin, entire formations are slaughtered. On August 17th, 1943, 60 B-17s are shot down over Schweinfurt and Regensburg. The P-47 escorts can't climb fast enough to prevent the massacre. By autumn 1943, the statistics are undeniable. German fighters typically attack from above, diving through formations at high speed, firing and climbing away before escorts can respond. The P-47's poor climb rate means it reaches combat altitude after the damage is done. Bomber crews die, while Thunderbolt pilots struggle upward through thin air, cursing their aircraft's weight and watching German fighters escape above them. Colonel Hubert Zemke, commanding the 56th Fighter Group, writes to 8th Air Force Headquarters on November 3rd, 1943, the P-47 achieves superior performance at altitude, but German tactics exploit our climb deficiency. We need more power below 25,000 feet, or we'll continue losing bombers. The response arrives November 19th. Materiel Command is investigating engine modifications. Continue current operations. But at Wright-Patterson's Army Airfield in Dayton, Ohio, a different conversation is occurring. One that will change everything. At Wright-Patterson Army Airfield's Materiel Command headquarters, the fuel problem becomes a crisis in December 1943. Lieutenant Colonel Marcus Cooper, chief of the fighter branch, spreads combat loss reports across his desk. The numbers tell a brutal story. Between August and November 1943, the 8th Air Force loses 321 heavy bombers to enemy action. German fighters account for 214 of those losses. The majority occur during the climb to target altitude or the initial bombing run, when T-47 escorts are still climbing to effective intercepting altitude. Cooper's staff calculates the tactical gap. German Bf 109G models climb at 3,000 feet per minute. Focke-Wulf 190 has managed 2,800 feet per minute. The P-47D, even with the improved R2800-63 engine, struggles to exceed 2,200 feet per minute. The difference is 800 feet per minute. In a 10-minute climb to 25,000 feet, German fighters gain 8,000 feet of altitude advantage. They can position above bomber formations, dive through at maximum speed, and climb away before American escorts arrive. The mathematics are simple. The solution is not. 3 approaches dominate the discussion. Republic Aviation proposes engine modifications to increase manifold pressure. Pratt and Whitney suggests water methanol injection to prevent detonation at higher boost settings. And a small team at Standard Oil's research facility in Bayway, New Jersey, proposes something more radical. A new fuel. The fuel team is led by Dr. Thomas Migley Jr., a chemist who pioneered tetraethyl lead as an octane booster in the 1920s. His assistant, Robert Harrington, has been experimenting with aromatic hydrocarbons, specifically blends of toluene, xylene, and isooctane, that achieve performance numbers far beyond 130. On December 7, 1943, Harrington presents his findings to Materiel Command. The fuel achieves a lean octane rating of 110 and a rich performance number of 150. In laboratory tests, it allows engines to operate at manifold pressures 15% higher than 100/130 fuel without detonation. The performance increase should translate to approximately 400 additional feet per minute of climb rate. The response is immediate skepticism. Colonel Raymond Davis, Chief of the Fuel Procurement Office, raises the first objection. Dr. Harrington, your fuel requires aromatic hydrocarbon production at scales we don't currently possess. Toluene production is allocated to explosives manufacture. Xylene production is limited. How do you propose we produce this fuel in quantities sufficient for operational use? Harrington's response is careful. Current production capacity could supply approximately 30 fighter groups with sufficient fuel for combat operations. We estimate 3 months to scale production for wider deployment. 3 months, Davis repeats. In 3 months, how many bomber crews will die waiting for your fuel? The room falls silent. Cooper leans forward. Dr. Harrington, I need a direct answer. Can your fuel be produced now in quantities sufficient for testing? Yes, sir. We can produce 5,000 gallons within 2 weeks. Then do it. We'll test with 1 fighter group. If it works, we'll find the production capacity. If it doesn't, we've lost 2 weeks and 5,000 gallons of experimental fuel. Davis shakes his head. Colonel, I must object. The procurement regulations require... Cooper cuts him off. The regulations require that we win this war. The 56th Fighter Group has the most experienced P-47 pilots in the European theater. We'll test with them. If Robert Johnson and Francis Gabreski can't make this fuel work, nobody can. On December the 22nd, 1943, Materiel Command issues testing authorization. The fuel receives the designation ANF 58. Standard Oil will deliver 5,000 gallons to RAF Boxted, the 56th Fighter Group's base in Essex, England. Testing will commence January 10th, 1944. Results will be reported by January 31st. The clock is running. But nobody at Wright-Patterson knows that the real obstacle isn't chemistry. It's the men who have to burn it. The first truck arrives at RAF Boxted on January 8th, 1944. Master Sergeant Ralph Safford, crew chief for Captain Gabreski's P-47, watches the tanker roll past the flight line. The fuel sloshes in transparent sight glasses. It's purple. Deep, unmistakable purple. What the hell is that? Safford asks. The truck driver shrugs. Orders say it's experimental fuel. 150 octane. We're supposed to segregate it from the regular supply. Safford walks to the operations-based shack where Colonel Zemke is reading the technical directive that arrived with the fuel shipment. The document is 32 pages of chemistry, engineering specifications, and warnings. Safford reads over his shoulder. Engine operating limits remain unchanged, Zemke reads aloud. Maximum manifold pressure 65 inches mercury, maximum RPM 2700, water methanol injection prohibited during testing phase. He looks up. They want us to test new fuel, but not change anything else. Doesn't make sense, sir. Safford says. If the fuel prevents detonation at higher boost, why can't we increase boost? Because, Zemke says slowly, they don't trust their own fuel yet. They want to see if it performs better at current settings before they authorize higher power settings. The testing protocol is conservative to the point of frustration. Phase 1 requires 10 flights at standard power settings to establish baseline performance. Phase 2 allows gradual increase in manifold pressure, 5 inches at a time, monitoring engine temperatures and performance. Phase 3, if engines survive, permits combat evaluation. Colonel Zemke assigns the testing to his most experienced pilots, Captain Francis Gabreski, 26 years old, 21 confirmed kills. Captain Robert S. Johnson, 23 years old, 15 confirmed kills. Major David Schilling, 25 years old, 16 confirmed kills. These men know the P-47's performance envelope better than the engineers who designed it. On January 10th, 1944 at 0830 hours, Gabreski climbs into his P-47D, serial number 4226418. The name Hun Hunter from Poland is painted on the fuselage. Safford has personally supervised every detail of the pre-flight inspection. The fuel tanks hold 375 gallons of Purple Passion. The auxiliary tank under the belly holds another 175 gallons of standard 130 octane, just in case. How does she feel? Safford asks from the wing. Gabreski runs through the checklist. Magnetos, fuel pressure, hydraulics, everything reads normal. Like any other fuel. Let's see if it burns different. The R-2800 ignites with its characteristic thunderous roar. Gabreski taxis to the runway, advances the throttle, and at 90 knots, pulls back on the stick. The Thunderbolt breaks ground and climbs. The difference is immediate. Gabreski's rate of climb indicator swings past 2,300 feet per minute. 2,500, 2,700. At 5,000 feet, he's climbing faster than he's ever climbed in a P-47 without water methanol injection. The engine temperature remains within normal limits. The manifold pressure holds steady at 65 inches, but the aircraft is ascending like it weighs 2,000 pounds less. He keys his radio. Keyworth leader to base, rate of climb at 5,000 feet, 2,700 feet per minute, engine temps normal. This is remarkable, Zemke's voice crackles back. Keyworth leader, continue to 15,000 feet, maintain current power settings. At 15,000 feet, Gabreski levels off and accelerates. The airspeed indicator climbs 340 miles per hour, 360, 380. He's 15 miles per hour, faster than his best previous performance at this altitude. He dives to 5,000 feet and climbs again. This time, they're timing the ascent carefully. 8 minutes and 40 seconds to reach 25,000 feet. His previous best time, with standard fuel, was 10 minutes and 30 seconds. He's gained 1 minute and 50 seconds, nearly 2 minutes faster to combat altitude. When he lands, 45 minutes later, the entire 56th Fighter Group is waiting. Zemke approaches before Gabreski even removes his oxygen mask. Talk, Zemke says. Gabreski climbs down, his hands still trembling with adrenaline. Colonel, that fuel is everything they promised and more. I've been flying jugs for 15 months. That wasn't the same airplane. Over the next 72 hours, 28 test flights confirm Gabreski's experience. The data is consistent across all pilots and all aircraft. ANF-58 fuel provides rate of climb increase 350 to 410 feet per minute depending on altitude. Top speed increase 14 to 19 miles per hour across all altitude bands. Service ceiling increase 1,600 feet, time to 25,000 feet reduced from 9.2 minutes to 7.1 minutes. But the most significant discovery comes from Captain Robert S. Johnson on January 13th. Johnson, known for aggressive flying and pushing aircraft to their limits, decides to test something the technical directive specifically prohibits. He advances his manifold pressure beyond 65 inches, 67 inches, 68, 70 inches of mercury. The R-2800 responds with a surge of power that slams him back against his seat. His rate of climb exceeds 3,000 feet per minute. At 72 inches, briefly, he touches 3,200 feet per minute. The engine temperature climbs but remains within acceptable limits. No detonation, no roughness. The purple fuel absorbs the abuse and begs for more. He lands and immediately seeks out his crew chief, Staff Sergeant Ralph Safford. "Sarge, that fuel can handle more boost than they're telling us. I pushed it to 72 inches for 30 seconds. The engine loved it." Safford's expression darkens. "Captain, with respect, you just violated the testing protocol. If Material Command finds out, they'll shut down the program. Then don't tell them, but adjust my wastegates. I want to be able to hit 70 inches without breaking protocol. The wastegate controls the turbo supercharger. If we set it to allow higher manifold pressure, I can claim it was a wastegate issue, not pilot error. It's a technical loophole. The wastegate, controlled by an actuator arm, determines how much exhaust gas drives the turbo supercharger. A looser wastegate setting allows higher boost. Officially, wastegates are set at the factory and locked. Unofficially, experienced crew chiefs know how to adjust them. Safford considers this. If I do this and something breaks, we're both in deep trouble. If we don't do this, Johnson says quietly, more bomber crews die. Those boys are counting on us to get above the Germans. This fuel gives us that chance. Let's not waste it. That night, after the flight line empties, Safford adjusts Johnson's wastegates. Similar quiet modifications occur across the 56th Fighter Group. Crew chiefs, who understand the stakes better than any regulation, begin tweaking their aircraft. The pilots don't ask questions. The ground crews don't volunteer information. By January 15th, at least 15 P-47s can achieve manifold pressures above 70 inches when needed. The combat test begins February 17th, 1944. The target is Brunswick, Germany. The mission involves escorting 153 B-17s deep into enemy territory. Intelligence reports expect heavy Luftwaffe resistance. The 56th Fighter Group launches 61 P-47s, including the first 16 aircraft fully fueled with ANF-58. The remaining aircraft carry standard 130 octane. At 28,000 feet, as Johnson's flight crosses the German border, the Luftwaffe appears. 40 Bf, 109 Gs, diving from 35,000 feet. Johnson advances his throttle past the stop. His wastegates, adjusted by Safford, allow the manifold pressure to surge to 70 inches. The climb rate exceeds 3,000 feet per minute. Within 90 seconds, he's level with the diving Messerschmitts. Within 2 minutes, he's above them. He rolls, inverted, and dives. His 8 50 caliber machine guns converging at 300 yards. The first Bf-109 disintegrates. He pulls up, using his speed to climb above the remaining German fighters. They break left, trying to escape. Johnson follows, maintaining altitude advantage throughout the engagement. When the fight ends 7 minutes later, the 56th Fighter Group claims 12 confirmed kills. Not a single B-17 is lost to enemy fighters during the bomb run. The purple fuel worked exactly as promised, better than promised. But the real test comes after landing. Johnson's P-47D is immediately impounded. Ground crews discover the modified wastegates. Safford is called to operations. Colonel Zemke confronts both men in his office. "Captain Johnson, your engine logs show manifold pressures exceeding testing protocol by 7 inches. Sergeant Safford, your maintenance logs show no wastegate modifications. One of you is lying. Both of you are in violation of direct orders." Johnson meets Zemke's stare. "Sir, with respect, my aircraft performed flawlessly. We shot down 12 Germans without losing a single bomber. The fuel can handle more than the protocol allows. I proved it." "You proved," Zemke says slowly, "that you're willing to risk court-martial to win a fight. That's either courage or stupidity. And I haven't decided which." He turns to Safford. "Sergeant, did you modify Captain Johnson's wastegates?" Safford hesitates. Then, "Yes, sir. Captain Johnson requested it. I complied." Zemke looks between them for a long moment. Then he does something unexpected. He smiles. "Good. Because I want you to modify every wastegate in the group. If this fuel can handle 70 inches of boost, we're going to use 70 inches of boost. I'll send a report to Materiel Command recommending they revise the protocol. In the meantime, we're going to keep killing Germans." The room erupts in grins. Johnson exhales. Safford nods. "One condition," Zemke adds. If an engine fails because of overboosting, you too personally explain to the pilot why his engine quit at the worst possible moment. Dismissed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The report reaches Wright-Patterson on February 23, 1944. Colonel Cooper reads Zemke's recommendation with a mixture of admiration and exasperation. The 56th Fighter Group has essentially conducted unauthorized combat testing of overboosted engines using experimental fuel. The results are undeniable: 12 kills, 0 losses, and performance that exceeds every projection. Cooper forwards the report to Pratt and Whitney with a single question: can the R-2800 survive sustained operations at 70 inches manifold pressure with AN-58 fuel? The response arrives within 48 hours. Pratt and Whitney engineer William Gwynne writes, laboratory testing confirms the fuel's anti-detonation properties allow manifold pressures up to 72 inches without engine damage. However, sustained high-boost operations will reduce time between overhauls from 400 hours to approximately 280 hours. This is an acceptable trade-off for combat performance gains. On March 1st, 1944, Material Command revises the testing protocol. P-47D models equipped with water methanol injection systems and burning AN-58 fuel are authorized to operate at 70 inches manifold pressure for combat operations. The new power setting produces approximately 2,600 horsepower, a 30% increase over standard operations. But the fuel supply remains limited. Standard Oil's Bayway facility can produce only 12,000 gallons per month, at consumption rates of approximately 200 gallons per combat sortie per aircraft. That's enough to support one fighter group for intensive operations. The 8th Air Force has 26 fighter groups. The solution comes from an unexpected source. In Abadan, Iran, the Anglo-Iranian Oil Company operates the world's largest oil refinery. The facility produces aviation fuel for British forces in the Mediterranean and Middle East. When the British Air Ministry receives intelligence about AN-58's performance, they immediately request the chemical formula. Standard Oil, under pressure from the US government, shares the formula with their British counterparts. The Anglo-Iranian facility begins production in March 1944. British chemists modify the formula slightly, increasing the water content and adjusting aromatic ratios. The result achieves performance numbers of 100/150, slightly different from the American 110/150, but operationally identical. The British fuel receives the designation 150 performance number or 150 PN. It's dyed purple, just like its American cousin. British ground crews immediately dub it Purple Passion, the same nickname American crews use. By April 1944, production reaches 45,000 gallons per month across both American and British facilities. 8th Air Force Headquarters faces a strategic decision. 26 fighter groups need fuel. Purple Passion can supply only 4 groups for intensive operations. Which groups receive priority? The decision is cold mathematics. The 4 highest-scoring P-47 groups receive priority allocation: the 56th Fighter Group at RAF Boxted, the 78th Fighter Group at RAF Duxford, the 352nd Fighter Group at RAF Bodney, and the 353rd Fighter Group at RAF Raiden. By May 1944, 300 P-47s are flying combat missions with Purple Passion. The performance impact is immediate and devastating to the Luftwaffe. On March 6, 1944, the 8th Air Force launches its first major raid on Berlin. 240 B-17s attack the German capital. The Luftwaffe responds with every available fighter, nearly 300 aircraft. German commanders expect to repeat the Schweinfurt massacre, where inadequate escort allowed them to slaughter bomber formations. Instead, they encounter P-47s that climb like their Bf-109s and dive faster than anything in the German inventory. Major David Schilling leading the 62nd Fighter Squadron, intercepts a formation of 40 Bf-109s at 32,000 feet. The Germans, confident in their altitude advantage, begin their attack run. Schilling's flight, burning purple passion, and operating at 70 inches manifold pressure, climbs through 35,000 feet before the Germans complete their dive. The Messerschmitts suddenly find themselves below the Americans. Schilling's flight dives through the formation, guns blazing. In the span of 4 minutes, they shoot down 7 German fighters. The remaining Bf-109s break off the attack and flee east. Similar engagements occur across the Berlin raid. P-47s, equipped with purple passion, destroy 38 Luftwaffe fighters. Only 6 B-17s are lost to enemy action during the bomb run. The difference from previous raids is stark. The bombers complete their mission. The crews come home. Luftwaffe pilot Oberleutnant Heinz Knoke writes in his combat diary on March 7, 1944, "The American Thunderbolts have changed. They climb to our altitude before we can complete our attacks. Their speed at altitude exceeds our Bf-109s. We can no longer dictate the terms of engagement. The Americans are everywhere, always above us." The psychological impact proves as significant as the tactical advantage. German fighter tactics since 1941 have relied on altitude superiority. Attack from above, dive through the bombers, zoom, climb away before escorts arrive. When that fundamental advantage disappears, the entire doctrine collapses. Luftwaffe aces, who survived 2 years of combat, suddenly find themselves at a disadvantage. Major Gunther Roll, with 275 confirmed kills, is shot down by a P-47 on April 12, 1944. He survives with severe injuries. In his post-war interview, he attributes his survival to bailing out before his aircraft disintegrated. "The Thunderbolt stayed with me through the entire dive. I could not escape. I could not outclimb it. I had no options except to bail out or die." The fuel makes the difference in ways that transcend simple performance numbers. In dogfights, altitude equals energy, energy equals options, options equal survival. Purple passion gives American pilots energy advantage for the first time in the European air war. By May 1944, the kill ratio shifts dramatically. P-47 units equipped with purple passion achieve kill ratios of 5.3 to 1. They destroy 5.3 German aircraft for every P-47 lost in combat. Units still using standard 130 octane fuel achieve kill ratios of 2.7 to 1. The difference is purple passion, but the fuel creates unexpected problems. On April 28, 1944, Lieutenant James Howard's P-47 suffers engine failure at 28,000 feet over Frankfurt. He glides to a rough landing in Allied-controlled territory near the Belgian border. When mechanics examine his engine, they discover something disturbing. The exhaust valves show severe erosion. The cylinder head temperatures exceeded safe limits during his last 3 sorties. The pistons display early signs of detonation damage. His engine, rated for 400 hours between overhauls, has accumulated only 212 hours. It's already failing. Pratt and Whitney investigates. The problem isn't the fuel, it's pilot behavior. Purple passion enables sustained high-power operations that were impossible with standard fuel. Pilots, accustomed to brief bursts of combat power followed by cruise settings, now maintain 70 inches of manifold pressure for extended periods. The engines can handle it briefly, but sustained operations at maximum power accelerate wear catastrophically. On May 3, 1944, 8th Air Force Headquarters issues new operating guidelines. Pilots may use 70 inches manifold pressure for combat engagements not exceeding 5 minutes per sortie. Extended operations at high boost are prohibited, except in emergency situations. The restriction frustrates pilots but preserves engines. By June 1944, the average time between overhauls stabilizes at 290 hours for Purple Passion operations, acceptable given the performance advantages. The D-Day invasion on June 6, 1944, becomes the ultimate test. The 9th Air Force, supporting ground operations, fields 37 P-47 groups. Every aircraft carries bombs or rockets in addition to ammunition. The weight penalty reduces performance, but 16 groups, equipped with Purple Passion, maintain climb rates sufficient to intercept any Luftwaffe response. The Luftwaffe sends 200 fighters against the invasion beaches. P-47s intercept them before they reached the landing zones. In one day, Thunderbolt pilots shoot down 63 German aircraft. Not a single Luftwaffe fighter successfully attacks the beaches. The Purple Passion groups account for 41 of the 63 kills. By July 1944, production of ANF-58 reaches 120,000 gallons per month, enough to supply 12 fighter groups. The expansion continues. By December 1944, production exceeds 400,000 gallons per month. Every P-47 group in the European theater has access to Purple Passion. The impact on the air war is undeniable. From June through December 1944, P-47 units destroy 3,200 German aircraft in air-to-air combat. The kill ratio averages 4.6 to 1 across all units. Purple Passion-equipped groups average 5.8 to 1. But the real measure of success isn't kills. It's bombers that complete their missions. From January through December 1944, the 8th Air Force loses 2,653 heavy bombers to all causes. Fighter-related losses account for 712 aircraft, a dramatic decrease from the 3,000-plus losses projected if pre-Purple Passion performance had continued. 712 crews die, but 2,300 crews live who would have died without Purple Passion. 23,000 men come home because chemistry changed the performance envelope of the P-47 Thunderbolt. The Germans notice. Captured Luftwaffe documents from late 1944 reveal desperate attempts to produce equivalent high-octane fuels, but Germany's synthetic fuel production, already strained by Allied bombing, cannot spare capacity for experimental fuels. The Luftwaffe continues flying with C3 fuel, equivalent to Allied 130 octane, through the end of the war. The fuel gap becomes insurmountable. By February 1945, German fighters avoid engagement with P-47s whenever possible. Luftwaffe pilots report that American Thunderbolts fly like they weigh half what they actually weigh. They don't know about Purple Passion. They just know the Americans have an advantage that cannot be overcome through skill or tactics. May 8th, 1945. Victory in Europe. The P-47 Thunderbolt has flown 746,000 combat sorties, more than any other American fighter. Of the 3,752 enemy aircraft destroyed by P-47 pilots, the vast majority fall to aircraft equipped with Purple Passion fuel. The total cost in American lives, 3,499 P-47s, lost in combat, with an estimated 1,123 pilots killed. But analysts at the Army Air Force's Evaluation Board estimate that without high-octane fuel improvements, losses would have been 40% higher. An additional 1,400 pilots dead, perhaps 5,000 more bomber crewmen lost due to inadequate fighter escort. The fuel makes the difference between air superiority and catastrophe. But the story of Purple Passion isn't just about combat victories. It's about the men who made it work, the chemists who formulated it, the refineries that produced it, the truck drivers who delivered it, the crew chiefs who adjusted wastegates and pushed boundaries, the pilots who trusted their lives to an experimental fuel that turned purple in the sunlight. Captain Robert S. Johnson finishes the war with 27 confirmed aerial victories and 91 combat missions. He never loses an aircraft to mechanical failure. His crew chief, Staff Sergeant Ralph Safford, maintains Johnson's P-47 through the entire campaign. When asked in a 1978 interview about the wastegate modifications, Safford's response is simple. We did what worked. The rulebook said 65 inches. Reality said 70 inches. We chose reality. Colonel Francis Gabreski becomes the highest-scoring American ace in Europe with 28 confirmed kills. He survives as being shot down on July 20th, 1944, spends 10 months as a prisoner of war, and returns home a legend. In his 1976 autobiography, he writes, The P-47 was always a good aircraft. With Purple Passion fuel, it became a great aircraft. The difference was night and day. Colonel Hubert Zemke, who commanded the 56th Fighter Group during the critical Purple Passion testing period, finishes the war with 17 3/4 confirmed kills. He's shot down over Germany in October 1944 and spends 7 months as a prisoner. After the war, he testifies before Congress about the importance of fuel research. His statement is blunt. Fuel determined performance. Performance determined survival. We won the air war because our fuel was better. But the true architects of Purple Passion never receive public recognition. Dr. Thomas Midgley Jr. dies in November 1944, 7 months before the war ends. His assistant, Robert Harrington, continues fuel research through the 1950s, eventually becoming chief chemist at Standard Oil. He never discusses his wartime work publicly. When contacted by aviation historians in 1972, his response is brief. We made fuel that helped pilots come home. That was the job. The production statistics tell the story of scale. From January 1944 through May 1945, American and British refineries produce 4.7 million gallons of high-octane aviation fuel rated at 150 performance number or higher. That fuel powers approximately 120,000 combat sorties. The cost per gallon, $3.47, compared to $1.12 for standard 130 octane fuel. The Army Air Force spends an additional $9.8 million on high-octane fuel during the final 16 months of the European War. The accountants call it expensive, the pilots call it essential, the bomber crews call it life-saving. The influence extends beyond World War II. When the United States Air Force forms in 1947, high-octane fuel research continues. The Korean War sees F-80 Shooting Star jets using water methanol injection for takeoff power boost. The principle remains identical. Increase power without increasing engine size. Modern aviation fuels trace their lineage directly to Purple Passion. The 100 low-lead fuel used in general aviation to date achieves octane ratings of 100 using tetraethyl lead additives developed during World War II. The chemistry evolved, but the fundamental principle remains. Fuel determines performance. The P-47 itself enjoys a distinguished post-war career. The aircraft serves with the Air National Guard until 1953. Multiple nations operate Thunderbolts through the 1950s. The final military P-47 is retired by the Peruvian Air Force in 1967, 24 years after the aircraft's combat debut. But perhaps the most powerful testimony comes from the men who flew against the Purple Passion Thunderbolts. Former Luftwaffe Major Johannes Steinhoff, who survived the war with 176 confirmed kills, speaks at a 1978 symposium on World War II aviation. An American veteran asks him about the P-47's performance in late 1944. Steinhoff's response is illuminating. The Thunderbolt in 1943 was dangerous, but manageable. We could outclimb it, outturn it at low altitude, and escape vertically if needed. The Thunderbolt in 1944 was a different aircraft. It climbed like our Bf-109s. It stayed with us through dives. It maintained speed at altitude better than any aircraft we flew. We couldn't understand what changed. The airframe looked identical, but the performance was superior in every measurable way. He pauses, then adds, "After the war, I learned about your fuel improvements. That explained everything. You didn't build a better aircraft. You fed the existing aircraft better fuel. The result was the same. We lost the air war." The lesson that resonates across decades. Innovation doesn't always require reinventing the machine. Sometimes it requires reimagining the fuel. Staff Sergeant Ralph Safford returns to his home in Ionia, Michigan in September 1945. He opens an automotive repair shop that operates until 1982. He never discusses his wartime service publicly. When a local newspaper interviews him in 1980 for a Veterans Day feature, he deflects questions about his role in the 56th Fighter Group. "I fixed airplanes," he says. "Other men flew them and fought the Germans. I just made sure the engines ran when they needed to run." The reporter presses him. "But didn't you work on experimental fuel testing?" Safford's response ends the interview. "I worked on keeping good men alive. The fuel was just part of that job." He dies in 1993 at age 81. His obituary mentions his military service in one sentence. No mention of Purple Passion, no mention of wastegate modifications, no mention of the role he played in changing the air war. But at his funeral, 3 men attend who traveled from different states specifically to be there. Former pilots from the 56th Fighter Group. They stand at attention during the service. They salute when the coffin passes. One of them, a retired airline captain who flew P-47s in 1944, speaks briefly at the graveside. "Ralph Safford taught me that rules exist until reality demands you break them. He adjusted my wastegates in February 1944 against regulations, against orders, against everything we were told to do. Because of that, I climbed high enough to intercept a German fighter that would have killed a bomber crew. I don't know their names, but they lived because Ralph did his job better than the rule book required." The fuel itself fades into history. By 1950, jet engines dominate military aviation. Piston engines and their exotic fuel requirements become obsolete. The refineries that produced Purple Passion convert to jet fuel production. The chemists who developed aromatic blends move to other projects. The formula becomes a footnote in technical manuals, but in the archives of the National Museum of the United States Air Force in Dayton, Ohio, a small display case contains a sealed glass vial. The label reads, ANF 58 Aviation Gasoline, circa 1944, also known as 150 pence or Purple Passion. The liquid inside still glows purple in the museum lighting. Next to the vial, a handwritten note in faded ink. "This fuel gave the P-47 wings it never had fuel. With it, we owned the sky. Without it, we would have lost the air war." Sometimes, chemistry matters more than courage. The note is unsigned, but handwriting analysis conducted in 2003 identifies it as belonging to Colonel Hubert Zemke. He, apparently, placed it in the display case during a museum visit in 1984, 2 years before his death. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.